Suppose you're at a casino, and the dealer offers a simple coin flip game. The pot starts at $2. A coin is flipped, and every time the coin lands on tails, the pot doubles. However, if the coin lands on heads, the game is over and you take home whatever is left in the pot. So if the first flip is heads, you walk away with $2. If the coin flips tails and then heads, you get $4. And if it flips tails twice and then heads, you get $8. In general, after k consecutive tails, followed by a heads, you get 2 to the k plus $1. Now here's the question. What is a fair entry price for the game? What would you be willing to pay? Naturally, you may only be willing to pay a moderate amount considering heads may show up quickly. But let's see what the math says. There is a probability of 1/2 that you win $2, 1/4 that you win $4, and 1/8 that you win $8, and so on. Each preceding outcome is less likely, but the payout is bigger and exactly the right proportion to keep contributing the same amount to the overall average. We may assume the casino to have infinite resources, and so we find the expected value of the game to be 1/2 times 2, plus 1/4 times 4, plus 1/8 times 8, and so on forever. Each term equals 1, and adding them up tells us the expected value of the game diverges to infinity. So while the math says that this game should be worth an infinite amount of money, in practice most people wouldn't be willing to pay more than a few dollars to play. This conundrum is at the heart of what we call the St. Petersburg paradox. The problem was first described by Nicolas Bernoulli I in a letter he sent to mathematician Pierre Raymond de Montmort. Later, in 1738, Daniel Bernoulli published an analysis of the problem in the commentaries of the Imperial Academy of Science of St. Petersburg. Because of this publication, the problem became known as the St. Petersburg paradox. The contradiction between the expected value of the game and what people are willing to pay to play the game raised serious questions about the fate of probability theory as a whole and the use of expected value in decision-making. In the 18th century, expected value was becoming a standard way to guide decisions about gambling, insurance, and finance. If it led to absurd conclusions in the St. Petersburg paradox, then how could people trust it elsewhere? Daniel Bernoulli recognized this problem, and it's what motivated him to rethink how value should be measured, leading to the idea of utility, which we will explore in a bit. And the paradox still resonates today. Lotteries are a perfect example. The expected value of a ticket might look favorable once jackpots are large enough, but very few people would ever treat them like a guaranteed investment. Or consider investing in a high-risk startup. Mathematically, the possibility of an enormous payoff can dominate the expected value, but in practice, most investors hedge or diversify because they recognize the risk involved. That's what makes the St. Petersburg paradox so important. It's not just mathematical curiosity, rather it highlights the gap between formal models and how people actually make choices under uncertainty. There have been many proposed solutions to the paradox, each trying to capture what the true value of the game should be. The most famous solution comes from Daniel Bernoulli, who argues that a gain of the same amount can feel completely different depending on how much you already have. As Bernoulli put it, the determination of the value of an item must not be based on the price, but rather on the utility it yields. There is no doubt that a gain of 1,000 ducats is more significant to the pauper than to a rich man, though both gain the same amount. Bernoulli proposed that the utility of increasing wealth follows a logarithmic curve where W is the total wealth of the gambler. So the utility function rises quickly at first and then gradually flattens as your wealth increases. This is what economists call diminishing marginal utility. The richer you are, the less each gain is worth to you in practical terms. So Bernoulli ultimately argued that the value of a gamble shouldn't be based on the expected money you might win, but on the expected utility gained from playing the game. For every possible outcome k, we can calculate the change in expected utility by subtracting the utility of your wealth before playing the game from the utility of your wealth after some outcome k. Each outcome has its own probability, so we multiply that change by the probability of that outcome and then take the sum over all possible k values. In other words, we're averaging over every possible result of the game. Since the game may in theory continue forever, we sum over an infinite number of outcomes k. The probability of each outcome is 1 over 2 raised to the power of k. The utility at the start of the game is just the log of your wealth, and the utility after playing the game is the log of your initial wealth plus 2 to the power of k, which is the payout from outcome k, minus c, the cost of playing the game. So this is the final expression for calculating the change in expected utility from playing the game. Remarkably, the expected value no longer blows up to infinity, so this expression gives a more realistic way to approximate the value of the game. We want to have a positive change in expected utility, otherwise the cost is not worth it. So for a person with wealth W, we may increase the cost C more and more until the change in expected utility is 0, and that is the maximum that person should pay to play the game. For example, a person with a wealth of $1 million would want to pay at most $20.88. A person with $1,000 would want to pay at most about half that, $10.95. And a person with only $2 may actually want to borrow more money to play the game, paying a cost up to $3.35. So, by redefining value through utility, Bernoulli managed to turn an infinite expectation value into something finite, a result that actually makes sense for human decision-making. But not everyone agreed that the key to answering the paradox is reconsidering how we measure value. Some people, including Nicholas Bernoulli himself, thought the problem wasn't with value at all, but with how people perceive probability, an idea we now describe as probability weighting. After all, the extreme payouts in this game depend on events that are extremely unlikely. Maybe this paradox disappears once we recognize that people simply don't treat small probabilities the way the equations say they should. In this view, the paradox isn't really about infinite values at all, it's about how we weigh uncertainty. People naturally discount extremely rare outcomes, so the massive payouts at the far end of the St. Petersburg game barely factor into our decisions. This approach reframes the paradox as a question of perception rather than calculation. The numbers might allow infinite winnings, but our sense of probability doesn't. If you apply that logic to the St. Petersburg game and simply cut off outcomes with less than a 1 in 10,000 chance, the expected payoff drops to about $13, a perfectly reasonable number and nowhere near infinity. Along a similar line of thinking, we may consider the fact that no casino will ever have an infinite amount of resources. At some point, the bank runs out of money and the game has to end. Let's call the casino's total wealth capital W. That's the total amount of money it could possibly pay out. The earnings after k rounds is 2 to the k plus $1, so the game can only continue as long as 2 to the k plus 1 is less than capital W. The maximum possible number of rounds, then, is the floor of log base 2 of capital W, which we can call L. The expected value of the game then turns out to be this value L. What this tells us is that even if the casino had $1 billion in reserve, the expected value of the game would only be about $30. And if the casino somehow had the combined GDP of the entire planet, it would still only increase to about $40 or $50. The St. Petersburg paradox began as a question about a coin flip, and it exposed something deeper about how we deal with uncertainty. But the paradox isn't just about probability, it's about the limits of reasoning itself. Thanks for watching. Please feel free to share your thoughts in the comments and subscribe to see more content like this in the future.